Hello everyone, my name is Chris Boffman. I'm one of the instructors here at the manufacturing program at COCC. This is chapter 1 of the Welding Principles and Practices book. You may not be getting this book your first class. You might be waiting until your second term. Make sure that you're devoted to the program before you pay money for the book. However, if you know you're going to continue to keep going through the program, I strongly suggest getting this book. You can use the video lectures, highlight things out of the book that I'm going to talk about and discuss along with going through the PowerPoint presentations. Now the PowerPoint presentations are available on Blackboard as well. I'll be able to go through this. I'm going to talk about some things that I feel are important, not just reading from the book, but also how they tie into everyday situations within welding and your career, moving through your career. Bear with me a little bit. We're just kind of starting out a new room. This is the first video we're doing. So let's talk a little bit about successful note taking, okay? So for example, here's a PowerPoint presentation. You're going to be able to find some of this stuff in your book as well. Most of the material out of it's the same. So I'm going to tell you which page it's on. I'm going to say, left-hand column, about halfway down. So for example, let me just start out doing it. Page 2, chapter 1. History of welding, left-hand column, it's going to start out overview. Now the second paragraph in starts out with the word welding, and basically I'll read from it and you can highlight that paragraph, or you can also look at it. We're going to hit the highlight and the bulleted points from the PowerPoint here. Okay, so let's start out. Welding is the joining together of two pieces of metal by heating to a temperature high enough to cause softening or melting, with or without the application of pressure, and with or without the use of filler metal. Any filler metal used has either a melting point approximately the same as the metals being joined, or a melting point that is below these metals but above 800 degrees Fahrenheit. So that's one paragraph that I started to read out of the book, and I might tell you that's a bulleted point. Now anything I read on these lectures, you want to highlight or take notes on, okay? So starting this year, we're probably not going to allow you to use the book. You're going to have to take handwritten notes. You can bring your handwritten notes in. You cannot type off the entire PowerPoint presentation. Okay? Handwritten notes only are allowed on the test, and we're going to stick with that throughout the program. Okay? So first thing, just what we read, welding is two pieces joining two pieces of metal by heating to a temperature high enough to cause softening or melting, with or without application of pressure, with or without use of filler metal. Melting point, same as metals being joined, or a melting point below metals, but about 800 degrees. So as we get more and more explanation, or more and more throughout the courses, we're going to start talking about different things. So what's the melting point of iron ore? You know, roughly 2800 degrees, 2780, 2790, right in there, degrees Fahrenheit. 800, 840 can be a very critical temperature between brazing versus soldering. These are all essential variables that matter within the welding technology field. Okay, so let's move on to the next one. Let's go to page number 3, underneath the history of metalworking. 1, 2, 3, 4, or the third sentence down, it starts out, the first metal to be worked was probably pure copper because it's a soft ductile metal that was widely available. Ductile, you see it highlighted, means easily hammered, bent, or drawn into a new shape or form. Okay? So this is hitting some high points, but notice we don't say anything about being ductile, correct? Okay, so let's go back. So not only is it some of your test questions may not just be off the PowerPoint, some of them might be off of things I talked about. So for example, ductile is a bulleted item. You need to understand what ductile means, okay? And let's read it again. You can always look back in the definitions as well, but ductile means easily hammered, bent, or drawn into a new shape or form. Okay? So let's skip down 1, 2, 3 sentences. Right-hand part of that column, it starts out and it says more than 4,000 years ago. Okay? Again, more than 4,000 years ago, copper mines on the peninsula of Sinai and the island of Cyprus were worked. I may not have pronounced them correct. Welding began more than 3,000 years ago when hot or cold metals were hammered to obtain a forged weld. Forged metals, bronze and iron, are mentioned in the Old Testament. So you may get a question asked that says welding began more than 2,000, 3,000, 4,000 years ago. Okay? In this case, according to the text, it was more than 3,000 years ago, even though at the beginning of the sentence or the paragraph it stated more than 4,000 years ago. Okay? Here we talk about began when people found they could shape rocks by chipping them with other rocks. Copper probably first metal to be worked. Here we're talking about ductile. Okay? Easily hammered, bent, or drawn. It was dated in Egypt as early as 4,000 BC and USA before 2000 BC. Welding began more than 3,000 years ago. Hot or cold metals hammered to obtain a forge weld. Again, it was written into the Old Testament. Next paragraph. Archaeologists have determined that bronze was developed sometime between 3,000 and 2000 BC. Iron became known to Europe about 1000 BC. Several thousand years after the use of copper. So we talk about the Bronze Age, we talk about the Iron Age. This gives us a little bit of perspective as far as what timeline it was there. Okay, so bronze was developed between 3,000 and 2,000. Iron became known to Europe about 1000 BC. The Philistines had 4 iron furnaces about 1300 BC, produced swords, chisels, daggers, and spearheads. Egyptians began making iron tools during the period of 900 to 850 BC and replaced bronze as metal used in manufacture of utensils, armor, and other applications. Part of the reason why is because iron is a lot harder material. It's not so, we just talked about ductile. Bronze was a very ductile iron. It's easily bent, hammered, and forged. So it's a lot softer material than iron itself was. So for an example of armor, you want a really hard material there to be able to keep spears, arrows, swords, and so forth from penetrating into it. If it was really soft, it would eventually get thin and break through, costing you your life at that area and at that era. All right. Next paragraph, the famous Damascus swords and daggers made in Syria about 1300 BC. Okay? They were sought after because of their strength and toughness, made by forged welding iron bars of different degrees of hardness, drying them down and repeating process many times. The working of metals followed one another in great ancient civilizations. Okay, let's take a break for a second. We start out working of metals so let's just make sure that we're on the same page here. This was one paragraph that started talking about famous Damascus swords and daggers. It's on page 3, okay, right-hand column. It's the second paragraph from the bottom, second paragraph up. You can follow along the bullet points in your book. So if I was you, I would highlight that entire paragraph and what it talked about here, along with the PowerPoint, okay? Now the last paragraph starts talking about the working of metals, followed one another into great ancient civilizations, okay? The book reads, the working of metals, copper, bronze, silver, gold, and iron, followed one another into the great ancient civilizations. By the time of the Roman Empire, the use of iron was common in Europe, the Near East, and the Far East. The Chinese developed the ability to make steel from wrought iron in AD 589. The Belgians were responsible for most of the progress made in Europe due to the high degree of craftsmanship developed by their workers. By the 8th century, the Japanese manufactured steel by repeated welding and forging and controlled the amount of carbon and steel by the use of fluxes. They produced the famous samurai sword with a blade of excellent quality and superior workmanship. If you get a chance, there's another one out there that it was called the Ufberg sword. There's a public PBS, Public Broadcast Systems, video out there. You can go online and find it. It's free to look it up, and it's the documentary is actually called The Viking Sword. Really great video. It really starts to explain the metallurgy within it and how much work went into forging of swords, materials, and so forth, especially in that era. Okay, so now we're on page 4, chapter 1, second paragraph down. Biggest thing that I want to focus on here is the blast furnace developed for melting iron about 1000 to 1200 AD. Now we just went back, we talked about iron was found in Europe 1000 BC, roughly 1300 BC as well. And now we're talking about the blast furnace was developed almost 2,000 years later, okay? So there was a long era there to where forge welding was the only type of welding that was being used in the world. With the addition of blast furnaces, now we're able to start getting different qualities out of iron and steel than, well, making steel, because steel is iron and carbon. We're starting to get better qualities out of the material that we were manufacturing at that time, which seen a huge benefit to a lot of soldiers, countries, equipment, so forth, okay? 14th and 15th centuries saw great improvements in design of blast furnaces. First cast iron cannon produced in the early 1600s. The Industrial Revolution in the middle of the 18th century brought many improvements. History of metalworking. The present factory system of mass production introduced. American was Eli Whitney, developed the idea of interchanging parts and manufacture of arms. Okay, let's back up. Let's look at our book. Okay, we're on page 4, left-hand column, halfway down underneath, the early developments in welding. Okay, paragraph above that, this is where we're still at, about halfway through the paragraph above early developments in welding. You see him start talking about Eli Whitney, the development of interchanging parts and manufacture of arms. Okay. Working of dies and molds became commonplace by beginning of the 19th century. We still use that today. It speeds up the process. Jigs, fixtures, dies, and molds. Very important. Henry Ford involved in developing the assembly line method for manufacturing automobiles early in the 20th century as well. All right. So, let's go to chapter 1, page 4, early developments in welding. At the beginning, this is a bulleted item, at the beginning of the 19th century, Edmund Davy discovered acetylene, a gas that was later used in oxyacetylene welding, heating, and cutting. The electric arc was first discovered by Sir Humphrey Davy in 1801 while he was conducting experiments in electricity. These inventions were forerunners of present arc welding processes. The first documented instance, sorry, I'm going to stop right there. Next paragraph down, the first documented instance of fusion welding was done by Auguste de Maritines in 1881. He welded lead battery plates together with a carbon electrode. This entire next paragraph, this entire next page is just a highlighted item I want you to read through. It's very fascinating. You're going to see 1 or 2 questions out of it. Mainly they will be coming off of this PowerPoint, but a little bit out of my lecture as well. Okay. 2 of August's pupil. I believe it's Nicholas. Let me look at the book here. Oh, it doesn't say. N. Bernardos and S. Olszewski saw the possibilities of this discovery and experimented with the arc powered by batteries that were charged from high voltage dynamos. Okay? Using carbon electrodes and electric power source 4 years later. Primary goal was to repair things so you didn't have to redo that. Out of the book, after 4 years of work, they were issued a British patent for a welding process using carbon electrodes and an electric power source.
Applications of the process included the fusion welding of metals, cutting of metals, and the punching of holes in metal. Okay, we're going to skip over to page 4, right-hand column, first full paragraph down. It starts out, bare metal electrode welding was introduced in 1888 by N.G. Slavianov, a Russian. His discovery was first recognized in Western Europe in 1892. C.L. Coffin was one of the pioneers of the welding industry in the United States. In 1889, he received a patent on the equipment and process for flash butt welding. And we'll talk about that later on as you're going through the career, or through the program, okay? So just real quick, Slavinov was the first recognized in Western Europe in 1892. So you might see something on the test that said, who was the pioneer of welding in the United States? C.L. Coffin was. However, he was not the first one. Slavinov, the Russian, had discovered it in Europe, in Western Europe in 1892. Well, they got the our years backwards on that, don't they? So let's read through here. By the turn of the century, welding, in 1890 he received additional patents for spot welding equipment. In 1892, working without knowledge of Slavinov's work, he received a patent for the bare metal electrode arc welding process. By the turn of the century, welding was a common method of repair. Highlighted especially at this time, welding was given added impetus by the development of the first commercial oxyacetylene welding torch by two Frenchmen, Fourche and Picard. Bare electrode welding became the prevailing electric arc welding method used in the U.S. until about 1920. So, here we talked about electric arc welding method used in the U.S. till about 1920. It was handicapped because of welds produced by these electrodes not as strong as metal being welded. Welding arc was very unstable. Remember, this was the beginning of the shielded metal arc welding electrode. So it didn't have the flux on it to help stabilize it. It was just a bare metal wire that they started welding with. Okay. Next paragraph, let's go down 1, 2, 3, 4 sentences in the center. Starts out, it says, in 1907, Schellberg, a Swedish engineer, received a patent covering the electrode coating process. The coating was thin and acted only as a stabilizer of the arc rather than as a purifier of the weld metal. Produced welds a little better than bare electrodes, but again, not quite to the level that we're seeing today. Okay? In 1912, Schellberg received another patent for electrode with heavier coating made of asbestos with binder of sodium silicate. In 1908, Bernardo's patented electroslag process of welding thick plates in one pass. And that's kind of a bolded item because the electrode here in bold, electroslag is a process that's different than shielded metal arc welding. Electroslag typically welds from the bottom to the top. So it's very similar to, say you have two really hot pieces of material, you have them formed, bring them together, and then you add a filler metal and you just watch it fill up. So basically your filler metal is going to start from the bottom and it's going to fill all the way up. Okay? So that's one pass. It's considered one weld. If you had the correct amount of material there, it would weld and fuse all the way at one time. We'll talk more about this through other chapters as well. So don't get too hung up on exactly what it is, but you can always research it if you want. Okay? All right. Chapter 1, page 5, reading out of the book now. Left-hand column, it starts out at the end of World War I. welding was widely accepted. Research on coated electrodes through the 1920s resulted in electrode coatings and improved core wire. This significant development was the main reason for the rapid advancement of the stick welding process. This term has now been superseded by the term shielded metal arc welding, what we use today most commonly, especially in nasty weather conditions. It's not affected by wind, rain, so forth. All right, keep going. I'm reading off the PowerPoint now. So by the end of the war, the welding was widely accepted. Okay, out of the book. Development of modern welding. I want you to read that first paragraph by yourself. Might be a question that comes out of there, so I want you to pay attention to what's in there. Second paragraph, so we are on page 5, chapter 1, right-hand column, second paragraph down, starts out with World War II. Okay, World War II spurred the development of inert gas welding, thus making it possible to produce welds of high purity and critical application. A patent was issued in 1930 to Hobart and Devers for the use of the electric arc within an inert gas atmosphere. Trying to figure out where my PowerPoint ties into my book here. Give me 1 second. Here we are. The patent was issued in 1930 to Hobart and Devers. Okay, it was not well received because, off the PowerPoint, it was not well received because high cost of argon and helium and lack of suitable torch equipment. Now, argon and helium are pretty easy to get. At that point in time, you couldn't run down to Airgas or Norco or Oxarc and just pick up a bottle for $100. All right. Paragraph below that starts out, Russell Meredith. Now, let's back up and talk about this real quick off of the PowerPoint, okay? So, tungsten electrode replaced magnesium procedure. Patent was issued in 1942. Yeah, we're going to talk about it with the book as well. So when we talk about with inert gas atmosphere, so what we're talking about now is going to be gas tungsten arc welding, gas metal arc welding, so forth. So we're using the TIG torch and an inert gas to help stabilize and shield the weld puddle. With gas metal arc welding, commonly known as MIG, same thing. So around this era was when it was first started, or getting more modernized, I should say. So we're going back to the book, page 5, right-hand column, halfway down. Russell Meredith, an engineer for the Northrop Aircraft Company, was faced with the task of finding an improved means of welding aluminum and magnesium in the inert atmosphere. Because of the high burn-off rate, the magnesium procedure was replaced by a tungsten electrode, and a patent was issued in 1942. Later, in 1942, the Linde Company obtained a license to develop the gas tungsten arc welding